Picture a cosmic maternity ward, where vast nurseries of gas and dust give birth to suns. This celestial cradle stretches across light years, dwarfing our earthly scale. Here, in the depths of space, new stars are born every moment, each with the potential to become the center of its own solar system. In this cosmic nursery, gravity plays the role of midwife. It gently coaxes and compresses the ethereal clouds, slowly but inexorably drawing matter together. As the pressure builds, temperatures soar, setting the stage for an astronomical miracle. And then, in a flash of brilliance, nuclear fusion ignites. This is the first cry of stellar life, a burst of energy that will sustain the newborn star for millions or even billions of years. It's a process as beautiful as it is powerful, marking the beginning of a cosmic journey that shapes the very fabric of our universe. Welcome, stargazers and cosmic explorers, to the incredible journey of stellar birth. We're about to witness the creation of the beacons of our universe, the stars that light our night sky and fuel the imagination of humanity. Now let me ask you this. What if I told you that at this very moment, thousands of stars are being born in our galaxy alone? It's not science fiction. It's the awe-inspiring reality of our dynamic universe. The Milky Way, our cosmic home, is a stellar nursery on a grand scale, constantly bringing new suns into existence. But that's just the beginning. Consider this. Every grain of sand on Earth represents only a fraction of the stars that exist in the observable universe. The number of stars out there is so vast that it challenges our ability to comprehend it. We're talking about hundreds of billions of galaxies, each home to hundreds of billions of stars. It's a cosmic ocean of stellar birth and life that stretches beyond our imagination. Today, we're going to unravel the mystery of how these gigantic fusion reactors come into existence. We'll journey from the vast, cold clouds of interstellar space to the heart of newborn stars, where temperatures reach millions of degrees. We'll witness the delicate dance of physics that transforms wisps of gas into the engines that light up the cosmos. Are you ready to explore the birthplaces of stars? To understand the forces that shape our universe? To see the cosmos in a new light? Then, let's begin our voyage into the stellar nurseries of space. If this journey through the cosmic nursery has ignited your curiosity like a newborn star, you're on the right track. Keep exploring the wonders of the universe with us at Exploring the Universe. Don't forget to leave a like on this video and subscribe to our channel for more journeys through the life cycle of stars and other fascinating cosmic phenomena. Together, let's continue to unravel the mysteries of the cosmos, one star at a time. Nebulae are the cosmic cradles where stars are born. These vast, ethereal structures are fundamental to understanding the process of star formation and the cycle of stellar life in our universe. Nebulae are enormous clouds of gas and dust that float in the vastness of space. These celestial formations can span hundreds of light years across, dwarfing our solar system in comparison. They come in various shapes and sizes, from wispy, serpentine structures to dense, compact regions. The word nebula comes from the Latin for cloud or fog, which aptly describes their appearance when viewed through telescopes. Some nebulae are visible to the naked eye as hazy patches in the night sky, while others require powerful instruments to observe. The composition of nebulae reflects the fundamental building blocks of our universe. Hydrogen. This is by far the most abundant element in nebulae, typically accounting for about 75% of their mass. Hydrogen is the simplest and most common element in the universe, and it plays a crucial role in star formation. Helium. The second most abundant element, helium makes up about 23 to 24% of a nebula's mass. Together with hydrogen, these two elements constitute the primary fuel for future stars. Heavier elements. The remaining 1 to 2% consists of heavier elements like oxygen, carbon, nitrogen, and traces of metals. These elements, often referred to as metals by astronomers, were forged in the hearts of previous generations of stars and dispersed into space through stellar winds and supernova explosions. Dust, tiny solid particles primarily composed of carbon such as graphite and silicates, make up a small but significant portion of nebulae. Despite their small contribution to the overall mass, these dust particles play a crucial role in star formation by helping to cool the gas and providing surfaces for chemical reactions. Several nebulae have captured the imagination of both scientists and the public due to their beauty and importance in star formation. Orion Nebula, M42, located about 1,344 light-years from Earth, visible to the naked eye as a fuzzy patch in the constellation Orion, one of the most studied star-forming regions containing hundreds of young stars, home to the famous trapezium cluster of hot, young stars. Eagle Nebula, M16, about 7,000 light-years away in the constellation Serpens, famous for its pillars of creation, towering columns of gas and dust. These pillars are active star-forming regions, sculpted by the intense radiation from nearby young stars. Cradle Nebula, M1, approximately 6,523 light-years from Earth in the constellation Taurus, the remnant of a supernova explosion observed by Chinese astronomers in 1054 before Christ. While not currently forming new stars, it demonstrates the cycle of stellar life and death that enriches nebulae with heavier elements. These nebulae, along with countless others, serve as true cosmic maternity wards. They provide the raw materials and conditions necessary for star formation, playing a crucial role in the ongoing stellar life cycle of our galaxy and beyond. Understanding nebulae is key to grasping the processes of star formation and the broader cycle of matter in the universe. As we continue to study these stellar nurseries, we gain deeper insights into our cosmic origins and the fundamental processes that shape our universe. The birth of stars is not a spontaneous event, but rather a process initiated by specific cosmic occurrences. Understanding these triggers helps us comprehend the complex interplay of forces in the universe that lead to the formation of new stars. Various cosmic events can serve as catalysts for star formation. Nearby supernovae. When a massive star explodes as a supernova, it releases an enormous amount of energy. The shock waves from this explosion can travel vast distances, compressing nearby nebulae. This compression increases the density of the gas and dust, potentially triggering the collapse necessary for star formation. The supernova that created the Cradle Nebula likely triggered star formation in neighboring regions. When galaxies collide or pass close to each other, their gravitational interactions can cause significant disturbances. These disturbances can compress gas clouds, initiating star formation. Colliding galaxies often experience bursts of star formation, known as starbursts. The antennae galaxies, NGC 4038/NGC 4039, are a prime example of colliding galaxies with enhanced star formation. In spiral galaxies, density waves move through the galactic disk like ripples on a pond. As these waves pass through regions of gas and dust, they compress the material, potentially triggering star formation. This process contributes to the distinct spiral arm patterns we observe in many galaxies. The intense radiation and stellar winds from massive, hot stars can compress nearby gas clouds. This triggered star formation can lead to a cascading effect where newly formed stars trigger the formation of even more stars. Once a disturbance has increased the density of a region within a nebula, gravity takes center stage. If the density of a region surpasses a critical threshold, its self-gravity becomes significant. At this point, the region's own gravitational attraction begins to overcome the outward pressure from gas temperature and turbulence. As gravity takes hold, the cloud begins to collapse inward. The collapse accelerates as more mass is drawn toward the center, increasing the gravitational pull. This process is known as free-fall collapse and marks the beginning of a protostar's formation. As the cloud collapses, any initial rotation it had is amplified. This leads to the formation of a flattened disk around the protostar, which will later play a crucial role in planet formation. Large nebulae rarely form just a single star. Instead, they typically fragment into multiple regions of star formation. The gene's mass is the minimum mass required for a gas cloud to collapse under its own gravity. Regions exceeding the gene's mass will begin to collapse, while those below it will remain stable. This leads to the fragmentation of large clouds into smaller, collapsing regions. Turbulent motions within the nebula can create density fluctuations. These fluctuations can seed the formation of multiple collapse regions. Magnetic fields can also influence this process, sometimes hindering collapse and other times channeling material to form dense regions. The fragmentation process often results in the formation of star clusters. These clusters can contain anywhere from a few dozen to thousands of stars, all born from the same parent nebula. The Pleiades and the Orion Nebula Cluster are well-known examples of such star clusters. In dense regions, protostars compete for the available gas and dust. This process can lead to a wide range of stellar masses within a single cluster, from small red dwarfs to massive blue giants. Understanding these triggers and processes gives us insight into the complex and dynamic nature of star formation in our universe. It's a testament to the interconnectedness of cosmic events, where the death of one star can lead to the birth of many others, and the collision of galaxies can ignite stellar nurseries across vast cosmic distances. The journey from a diffuse cloud of gas to a nascent star is a fascinating process that involves complex physics and dramatic changes in the structure and properties of the collapsing material. This transformation is a crucial stage in stellar evolution, setting the stage for the birth of a new star. Once the conditions are right for star formation to begin, gravity becomes the dominant force, initiating a process of collapse. The process starts with a portion of a molecular cloud that has reached a critical density. This region, often called a dense core, begins to collapse under its own gravity. As the collapse begins, it accelerates rapidly. The outer layers fall inward, gaining speed as they approach the center. This phase is often referred to as free-fall collapse because the inward motion is primarily driven by gravity. Initially, the collapsing cloud is transparent to its own radiation, allowing heat to escape easily. As the density increases, the cloud becomes opaque, trapping heat and slowing the collapse. Any initial rotation in the cloud is amplified as it collapses, due to the conservation of angular momentum. This leads to the formation of a flattened disk around the central, densest region. As the collapse progresses, the central regions of the cloud undergo dramatic changes. The density at the core increases dramatically, potentially by factors of millions or even billions. This process transforms the diffuse gas into a compact, stellar-like object. As material falls inward, it converts gravitational potential energy into kinetic energy and then into heat. The temperature at the core rises steadily from the cold temperatures of interstellar space, around 10 to 20 K, to thousands of degrees Kelvin. As the temperature and density increase, the internal pressure in the core rises. Eventually, this pressure becomes strong enough to slow and then halt the collapse of the innermost regions. When the internal pressure balances gravity, a stable, hydrostatic core forms. This marks a crucial transition in the star formation process. The formation of a protostar represents the first recognizable stage in the life of a star. A protostar is a very young, hot core that has formed within a collapsing molecular cloud. It's not yet a true star, as it hasn't reached the temperatures necessary for nuclear fusion. The protostar consists of a hot, dense core surrounded by a cooler envelope of infalling material. A disk of gas and dust, called a protoplanetary disk, often surrounds the protostar. At this stage, the protostar derives its energy primarily from gravitational contraction. As material falls onto the protostar, it releases gravitational potential energy, heating the object. Many protostars exhibit powerful jets of material ejected from their poles. These bipolar outflows help the protostar shed angular momentum, allowing further contraction. The protostar continues to accrete material from its surrounding envelope and disk. As it grows in mass, its core temperature and pressure continue to rise. This process continues until the core temperature reaches about 2000 K, at which point molecular hydrogen begins to dissociate. The protostar phase typically lasts for about 100,000 to a few million years, depending on the mass of the forming star. More massive protostars evolve faster than less massive ones. Protostars are typically hidden within dense clouds of gas and dust. They are best observed at infrared and radio wavelengths, which can penetrate the surrounding material. The formation of a protostar marks a crucial milestone in the star formation process. It represents the transition from a formless cloud to a distinct stellar object, setting the stage for the eventual birth of a new star. As we continue to study protostars, we gain valuable insights into the earliest stages of stellar evolution and the processes that shape our universe. The formation of a star is a constant struggle between the inward pull of gravity and the outward push of various forces. This cosmic tug-of-war shapes the destiny of the nascent star and its potential planetary system. At the heart of star formation lies a delicate balance between two opposing forces. Gravity constantly pulls the material of the protostar inward. This force increases as more mass accumulates at the center. If unchecked, gravity would cause the protostar to collapse into a singularity. As the protostar contracts, it heats up, increasing its internal pressure. This pressure pushes outward, counteracting the gravitational collapse. Sources of internal pressure include thermal pressure from the hot gas, radiation pressure from photons, degeneracy pressure in the densest regions. The protostar reaches a state of hydrostatic equilibrium when these forces balance. This balance is dynamic and can shift as the protostar evolves. The interplay between gravity and pressure determines the protostar's size and temperature. As the protostar continues to contract, its core temperature rises. When the core reaches about 10 million Kelvin, hydrogen fusion can begin. The onset of fusion marks the birth of a true star, ending the protostellar phase. Conservation of angular momentum. As the molecular cloud collapses, any initial rotation is amplified. This is due to the conservation of angular momentum, similar to a spinning ice skater pulling in their arms. The amplified rotation causes the infalling material to flatten into a disk around the protostar. This disk, known as a protoplanetary disk or proplet, can extend for hundreds of astronomical units. The disk is typically denser and cooler than the central protostar. It consists of gas, mainly hydrogen and helium, and dust particles. The inner regions are hotter and more turbulent, while the outer regions are cooler and more stable. The protoplanetary disk is the birthplace of planets. Dust particles in the disk can collide and stick together, gradually forming larger bodies. Over millions of years, these can grow into planets, asteroids, and comets. Protoplanetary disks have been observed around many young stars. The Hubble Space Telescope and ALMA have provided stunning images of these disks. One of the most dramatic features of young stellar objects is the presence of powerful outflows. Jets are narrow, highly collimated streams of material ejected from the poles of the protostar. Bipolar outflows are wider, less collimated flows of gas also emanating from the polar regions. Jets and outflows are thought to be driven by the interaction between the protostar's magnetic field and the rotating disk. Material is accelerated along magnetic field lines and ejected at high speeds. Jets can extend for several light years into space. They often exhibit a knotty structure with periodic bright spots called Herbig-Haro objects. Outflow speeds can reach hundreds of kilometers per second. Jets and outflows help remove angular momentum from the system, allowing material to continue falling onto the protostar. They interact with the surrounding molecular cloud, potentially triggering further star formation. These outflows are a key signature of the star formation process, often visible when the protostar itself is obscured. Jets and outflows have been observed across the electromagnetic spectrum, from radio to X-rays. Famous examples include HH30 in the Taurus molecular cloud and HH47 in the Gum Nebula. If this journey through the cosmic nursery has ignited your curiosity like a newborn star, why not continue to shine with us? Like this video and subscribe to our channel for more stellar adventures. Together, we'll explore the wonders of the universe, from the birth of stars to the mysteries of black holes and beyond. Join our cosmic community and let your curiosity burn as bright as the stars we study. The onset of nuclear fusion marks a pivotal moment in a star's life, transforming it from a protostar into a true star. This process is the engine that powers stars, allowing them to shine for millions or billions of years. As the protostar continues to contract under gravity, its core temperature steadily rises. The critical temperature for hydrogen fusion is approximately 10 million degrees Celsius, 18 million degrees Fahrenheit. In addition to high temperature, the core must also achieve sufficient density. At these extreme conditions, electrons are stripped from atoms, creating a plasma. Protons naturally repel each other due to their positive charge. The extreme temperature and density provide enough energy to overcome this repulsion. Even at 10 million degrees, most protons don't have enough energy to overcome the repulsive force directly. Fusion becomes possible thanks to quantum tunneling, which allows particles to tunnel through energy barriers. This is the primary fusion process in stars like our Sun and smaller. It involves a series of reactions that convert 4 hydrogen nuclei into 1 helium nucleus. 2 protons fuse to form deuterium, releasing a positron and a neutrino. The deuterium fuses with another proton to form helium-3. 2 helium, 3 nuclei combine to form helium-4, releasing 2 protons. 3. Energy release. Each completed cycle releases about 26.7 MeV of energy. A tiny amount of mass is converted to energy. Following Einstein's equals mc superscript 2 in stars more massive than the Sun, the carbon-nitrogen-oxygen cycle becomes dominant. It uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen into helium. When fusion begins, it provides an outward pressure that balances gravity. This marks the star's entry onto the main sequence. Energy produced in the core is transported outward through radiation and convection. It eventually reaches the surface, causing the star to shine. The onset of fusion often coincides with the development of a stellar wind. This wind blows away remaining envelope material, revealing the new star. The star becomes visible in optical wavelengths as surrounding gas clears. Its spectrum shows characteristics of a young, active star. Young stars go through several stages before reaching maturity. Understanding these stages helps astronomers trace the evolution of stars and star-forming regions. T-Tauri stars are young, pre-main sequence stars with masses similar to or less than the Sun. They are typically less than 10 million years old. T-Tauri stars show irregular brightness variations. These fluctuations are due to ongoing accretion and stellar activity. Strong emission lines, particularly H-alpha. Presence of lithium, which is destroyed in older stars. T-Tauri stars often exhibit strong stellar winds and bipolar outflows. These phenomena help the star shed angular momentum. Classical T-Tauri stars, still actively accreting from a disk. Weak-line T-Tauri stars have mostly cleared their disks. The main sequence is the stage where stars spend most of their lives. Stars on the main sequence have achieved a stable balance between gravity and fusion pressure. Steady hydrogen fusion in the core, relatively stable luminosity and temperature. Main sequence stars form a distinctive band on this temperature-luminosity plot. The position on this band is primarily determined by the star's mass. The time a star spends on the main sequence depends on its mass. More massive stars burn fuel faster and have shorter main sequence lifetimes. Low-mass stars become red dwarfs, can stay on the main sequence for trillions of years, eventually cool to become white dwarfs without passing through a giant phase. Sun-like stars spend billions of years on the main sequence, eventually become red giants, end their lives as white dwarfs surrounded by planetary nebulae. Massive stars have short main sequence lifetimes, millions of years, become supergiants, end their lives in spectacular supernova explosions, may leave behind neutron stars or black holes. Initial mass determines the star's luminosity, temperature, and lifetime. It also influences the star's internal structure and fusion processes. Mass is the primary factor in determining a star's ultimate fate. Understanding these stages and classifications helps astronomers piece together the life cycles of stars and the evolution of galaxies. From the tumultuous T-Tauri phase to the steady burning of main sequence stars, Each stage provides crucial insights into the complex and fascinating world of stellar astrophysics. The formation of planetary systems is intrinsically linked to the process of star formation, offering a fascinating glimpse into the origins of our own solar system and the myriad of exoplanetary systems we've discovered. Protoplanetary disks are formed from the leftover material of star formation. They typically consist of gas, mostly hydrogen and helium, and dust particles. The disk can extend hundreds of astronomical units from the central star. The inner regions are hotter, containing refractory materials like silicates and metals. The outer regions are cooler, allowing for the presence of ices and more volatile compounds. Over time, the disk becomes less massive as material accretes onto the star or is dispersed by stellar winds. The disk's lifetime is typically a few million years. Protoplanetary disks have been observed around many young stars. Instruments like ALMA have provided detailed images of these disks, revealing structures like rings and gaps. Dust particles collide and stick together, forming larger bodies. As these bodies grow, their gravitational influence increases, allowing them to attract more material. This process can lead to the formation of planetesimals and eventually planets. In some cases, parts of the disk may become dense enough to collapse directly under their own gravity. This process is more likely to form gas giant planets in the outer regions of the disk. Planets can move from their original formation locations due to interactions with the disk or other planets. This explains the presence of hot Jupiters, gas giants orbiting very close to their stars. Rocky planets form in the inner disk where temperatures are too high for ices to condense. Gas giants form beyond the snow line, where ices can accumulate, allowing for faster growth. The final stages of planet formation involve collisions between large bodies. These impacts can significantly influence a planet's final composition and characteristics. Transit method, observing the dimming of a star as a planet passes in front of it. Radial velocity method, measuring the wobble of a star caused by an orbiting planet. Direct imaging, capturing actual images of planets, challenging but increasingly possible. NASA's Kepler Space Telescope revolutionized exoplanet detection, discovering thousands of candidates. It revealed that planetary systems are common in our galaxy. Hot Jupiters, gas giants orbiting very close to their stars. Super-Earths, planets larger than Earth but smaller than Neptune. Earth-like planets, rocky planets in the habitable zone of their stars. Astronomers are particularly interested in finding planets in the Goldilocks zone, where liquid water could exist on the surface. Missions like TESS are continuing the search for potentially habitable worlds. Upcoming telescopes like the James Webb Space Telescope aim to study exoplanet atmospheres in detail. The ultimate goal is to detect biosignatures that could indicate the presence of life on other worlds. The fate of a star is largely determined at birth, with its initial mass playing a crucial role in shaping its life cycle and ultimate destiny. Collapse of a molecular cloud, formation of a dense, hot core surrounded by an envelope of infalling material. T-Tauri phase, for low-mass stars' pre-main sequence stage characterized by variability and strong stellar winds. The longest phase of a star's life, where it fuses hydrogen in its core. Duration depends on the star's mass, ranging from millions to billions of years. 4 low to intermediate mass stars, red giant phase, followed by planetary nebula formation. 4 high-mass stars, supergiant phase, followed by a supernova explosion. The final state depends on the star's initial mass, white dwarf, neutron star, or black hole. Low-mass stars end their lives as white dwarfs. These are dense, Earth-sized remnants composed mainly of carbon and oxygen. They slowly cool over billions of years. Intermediate mass stars explode as supernovae, leave behind neutron stars. Neutron stars are incredibly dense, with the mass of the Sun compressed into a sphere about 20 kilometers in diameter. High-mass stars also end in supernova explosions, form black holes. Black holes are regions where gravity is so strong that nothing, not even light, can escape. Higher mass stars burn through their fuel more quickly and have shorter lifespans. They also undergo more complex fusion processes, producing heavier elements. Stars are the primary factories for element production in the universe. Hydrogen and helium were formed in the Big Bang, but heavier elements are created in stars. Main sequence: stars produce helium through hydrogen fusion. More massive stars can fuse helium into carbon and oxygen. Elements up to iron are produced through fusion in massive stars. Elements heavier than iron are primarily created in supernova explosions and neutron star mergers. Stellar winds and supernova explosions disperse these elements into space. This enriched material becomes part of the next generation of stars and planets. Over time, the proportion of heavy elements in galaxies increases. This process is crucial for the formation of rocky planets and the development of complex chemistry necessary for life. The elements essential for life, carbon, oxygen, nitrogen, etc., are all products of stellar evolution. In a very real sense, we are made of star stuff, as Carl Sagan famously said. Understanding the life cycles of stars and their role in cosmic chemical evolution provides us with a profound connection to the universe. It reveals how the very atoms that make up our world and our bodies were forged in the hearts of stars and dispersed through space, linking us intimately to the cosmic story of creation and transformation. As we contemplate the vast cosmic processes that lead to star formation, we are drawn to reflect on our place in the universe. Uniqueness in uniformity. While star formation follows general principles, each star's journey is unique. Variations in initial conditions lead to a diverse array of stellar types and systems. The stars we see at night each have a complex past, often invisible to the naked eye. Modern astronomy allows us to uncover these hidden narratives. Star formation continues throughout the universe. We are witnessing a process that has been ongoing for billions of years. The death of stars provides material for new star formation. This creates a continuous cycle of stellar generations. Stars, gas, and dust in galaxies form complex, interacting systems. The life cycles of stars influence the evolution of entire galaxies. The lifespan of stars ranges from millions to billions of years. This vast timescale provides perspective on our brief human existence. The processes of star formation and death are linked across vast distances. This interconnectedness reflects a fundamental unity in the cosmos. New telescopes and instruments will provide unprecedented views of star-forming regions. Improved computational models will enhance our understanding of the physics involved. Studying young stars and their protoplanetary disks will inform our understanding of exoplanet formation. This may lead to breakthroughs in the search for habitable worlds. Understanding star formation will help us model the earliest stars in the universe. This could provide clues about the cosmic dark ages and the reionization of the universe. Combining observations across the electromagnetic spectrum with gravitational wave detections may offer new insights into stellar evolution and death. As with all scientific endeavors, we must be prepared for unexpected discoveries that could revolutionize our understanding. If this journey through the cosmic nursery has ignited your curiosity like a newly born star, you're on the right path. Continue exploring the wonders of the universe with us at Exploring the Universe. Don't forget to like and subscribe for more journeys through the life cycles of stars and other fascinating cosmic phenomena. Remember, every time you look up at the night sky, you're witnessing a vast tapestry of stellar stories, births, lives, and deaths playing out across cosmic time. Each star holds secrets of our cosmic heritage, and together, we can unravel these mysteries. Join our community of stargazers and cosmic explorers as we continue to push the boundaries of our understanding of the universe. Whether you're a seasoned astronomer or just beginning your cosmic journey, there's always more to discover. From the fiery nurseries of stellar formation to the awe-inspiring deaths of massive stars, the universe never ceases to amaze. So, stay curious, keep exploring, and let's continue this incredible journey through the cosmos together.